Discovery in quantum materials could make electronics 1,000 times faster. Researchers at Northeastern University have announced a groundbreaking discovery in the field of quantum materials that could revolutionize electronics, potentially making them 1,000 times faster and more efficient. This significant advancement lies in the ability to switch the electronic state of matter on demand, enabling a material to transition between insulating and conducting states virtually instantaneously. The breakthrough. The research led by Alberto della Torre, an assistant professor of physics, has been published in the journal Nature Physics. The key innovation is a technique termed thermal quenching, which allows researchers to manipulate a quantum material known as 1θs2. By applying controlled heating and cooling, they can switch the material between a metallic conductive state and an insulating state. This transition can be reversed on demand, offering unprecedented control over the material's electrical properties. Currently, processors operate within the gigahertz range. But this new method could enable shifts to terahertz speeds, vastly enhancing computing capabilities. Della Torre emphasized that this speed of change could transform not only the speed of electronic devices but also their size, allowing for the replacement of traditional silicon components with much smaller and faster quantum materials. Implications for electronics. The ability to control whether a material conducts or insulates electricity instantaneously mirrors the function of transistors, which have historically paved the way for the miniaturization of computers, from room-sized machines to the compact devices we use today. Gregory Feet, a professor of physics at Northeastern and a collaborator on the project, noted that the research represents a leap toward achieving the highest level of control over material properties. Feet remarked, "Everyone who has ever used a computer encounters a point where they wish something would load faster. There's nothing faster than light. And we're using light to control material properties at essentially the fastest possible speed that's allowed by physics." The researchers achieved a hidden metallic state in 1θs2 at temperatures close to room temperature, a state previously only stable at cryogenic temperatures. This stability is crucial as it allows for practical applications in electronics, maintaining its programmed conductive state for months, an unprecedented achievement. Reducing engineering challenges. Traditionally, electronic devices have required both conductive and insulating materials along with complex interfaces between them. This new discovery simplifies the paradigm by allowing a single material to be controlled with light for both conduction and insulation. "We eliminate one of the engineering challenges by putting it all into one material," Feet explained, highlighting the potential for significant advancements in electronics design. The research builds upon earlier studies that utilized ultrafast laser pulses to temporarily change material conductivity, which typically lasted only fractions of a second and often required extremely cold temperatures. The stable conductivity switching achieved at higher temperatures represents a major advancement in the field of quantum mechanics. Future directions. As the demand for faster and more efficient electronics grows, the need for new paradigms in information storage and processing becomes increasingly critical. Feet pointed out that the current approach to semiconductors, which involves stacking components in 3 dimensions, has limitations. This makes the exploration of tiny quantum materials essential for future electronics design. The research at Northeastern University not only contributes to the understanding of quantum materials but also opens doors to revolutionary applications in computing and electronics. By innovating in materials, the researchers aim to address the challenges of modern technology and improve information storage and processing capabilities. Conclusion. In summary, the discovery made by the team at Northeastern University represents a significant leap forward in quantum materials research with the potential to reshape the landscape of electronic devices. The ability to control material properties with light and achieve stable conductivity at room temperature could lead to faster, more efficient electronics that surpass the limitations of current silicon-based technologies. As the field of quantum materials continues to evolve, the implications for computing and technology are profound, heralding a new era of innovation in electronics. The discovery by researchers at Northeastern University regarding quantum materials presents several counterintuitive aspects that challenge conventional understanding in electronics and materials science. Here are the key points highlighting the counterintuitive nature of this research. 1. Single material for dual functionality. Traditionally, electronic devices necessitate the use of distinct materials for conducting and insulating functions, often requiring complex interfaces for effective operation. The breakthrough discovery allows a single quantum material, specifically 1θs2, to switch between these two states on demand. This contradicts the long-standing practice in electronics design where multiple materials are essential, demonstrating that simplicity can arise from complexity at the quantum level. 2. Room temperature stability. The ability to achieve stable conductivity in quantum materials at close to room temperature is particularly surprising. Historically, many quantum materials exhibited desirable conductive properties only at cryogenic temperatures, making practical applications challenging. The research defies this expectation, indicating that high-performance quantum materials can exist and operate effectively under more accessible thermal conditions. 3. Speed of operation. The concept that electronics could become 1,000 times faster through this technology seems implausible at first glance, given the current limitations of gigahertz processor speeds. The expectation that a transition to terahertz speeds is feasible through controlling material states with light challenges the conventional wisdom regarding the fundamental limits of electronic speed and processing capabilities. 4. Use of light for material control. The idea of using light to manipulate the properties of materials for electrical conduction is counterintuitive because it suggests a level of control over material states that was previously thought to be unattainable. This contrasts with traditional methods of electronic control which rely on electrical signals, thereby introducing a novel paradigm in material science that leverages optical phenomena. 5. Revolutionizing silicon-based technology. The research suggests a paradigm shift away from silicon-based electronics, which have dominated the field for decades. The implication that these quantum materials might not only supplement but potentially replace silicon suggests a significant rethinking of what materials are viable for future electronic devices, challenging the entrenched belief in silicon's supremacy. 6. Long-term stability of states. The fact that the quantum material can maintain its programmed state for months introduces a counterintuitive perspective on the stability of quantum states. In many quantum systems, stability is fleeting and often requires extreme conditions. This finding suggests that practical applications could be developed from materials that were previously deemed too unstable for real-world use. 7. Engineering challenges simplified. By eliminating the need for a well-engineered interface between different materials, conductive and insulating, the research implies that significant engineering challenges may be mitigated through the use of advanced quantum materials. This counterintuitive notion suggests that the complexity of electronics design could be reduced, leading to simpler and more efficient manufacturing processes. In summary, the research conducted at Northeastern University challenges various established norms in electronics and materials science, presenting a compelling case for the potential of quantum materials to revolutionize technology in ways that were previously considered impractical or impossible. The implications of this discovery extend far beyond the immediate technical advantages, suggesting a fundamental shift in how we understand and utilize materials in electronic applications. The discovery made by researchers at Northeastern University regarding quantum materials has the potential to revolutionize electronics. Yet several nuances and implications may be overlooked by the general public. Here are the critical elements of the report that merit deeper consideration. 1. Thermal quenching technique. The method known as thermal quenching allows for the rapid switching between conductive and insulating states. While the basic premise may seem straightforward, changing material states on demand, the implications for controlling material properties at will are profound. This ability to manipulate states not only enhances performance but also simplifies the design of electronic devices. The significance lies in its potential to minimize the complexity of electronic circuits which currently rely on multiple materials and intricate interfaces. This could lead to more compact, efficient designs and faster processing speeds. 2. Stability at room temperature. One of the most significant aspects of this discovery is the achievement of a stable conductive state at near room temperatures. Previous research relied on extremely low temperatures for such effects, which limited practical applications. The ability to maintain this state for months represents a leap in stability and usability in real-world applications. This breakthrough can lead to devices that do not require the energy-intensive cooling systems traditionally associated with quantum materials, making them far more practical for everyday use. 3. Replacement of silicon. The potential for quantum materials to replace silicon components in electronics is often highlighted, but the broader implications of this transition are frequently underestimated. Silicon has been the backbone of the electronics industry for decades, and its limitations are becoming increasingly evident as demand for speed and efficiency rises. Quantum materials could usher in a new era of electronics that not only offers enhanced performance but also allows for the creation of entirely new types of devices and applications that are currently inconceivable. This shift could have ripple effects across industries from computing to telecommunications and beyond. 4. Terahertz speed potential. The transition from gigahertz to terahertz processing speeds is a significant milestone. While many may understand this as a mere numerical increase, the implications for data processing and transmission are vast. Terahertz speeds could facilitate data transfer rates that far exceed current capabilities, transforming how information is processed, stored, and transmitted. This leap could enable advancements in artificial intelligence, real-time data analysis, and more responsive computing environments, fundamentally altering the technological landscape. 5. Elimination of engineering challenges. The research indicates that this discovery could eliminate the need for multiple materials that must be carefully engineered to work in tandem. This simplification not only reduces manufacturing complexity but also lowers costs and increases reliability. For engineers, this means fewer points of failure and a more streamlined design process, which can accelerate the development and deployment of new technologies. 6. Broader implications for quantum mechanics. While the focus is on electronics, the findings also contribute to the fundamental understanding of quantum mechanics and material science. Achieving controlled conductivity at practical temperatures opens new avenues for research and innovation within the field of quantum materials. This could lead to further breakthroughs in quantum computing, where the ability to manipulate material states is crucial for developing functional qubits and other components. 7. Potential impact on information storage. The report mentions the need for a new paradigm in information storage and processing. As data generation continues to explode, current storage technologies are struggling to keep up. Quantum materials could provide the means to develop faster, more efficient storage solutions that can handle significantly larger volumes of data without the same energy costs associated with traditional methods. 8. Cultural and economic shifts. The transition towards quantum materials in electronics may also lead to cultural shifts in how technology is perceived and utilized. As devices become faster and more efficient, user expectations will evolve, creating a feedback loop that demands even more innovation. Economically, industries reliant on semiconductor technology may experience upheaval, necessitating a re-evaluation of workforce training and education to prepare for the changes in skills needed in a quantum-dominated landscape. In conclusion, the research done at Northeastern University is not just a technical advancement, it represents a paradigm shift in electronics and material science. The ability to control quantum states at room temperature with stability and speed opens doors to innovations that could redefine the future of technology. Understanding these implications is crucial as they extend far beyond the laboratory and into the fabric of everyday life and the global economy. The significance of this discovery is multifaceted, merging scientific discovery with practical applications that could shape the next generation of electronic devices and systems. The research conducted at Northeastern University regarding quantum materials presents several significant insights that warrant in-depth analysis. Here are 4 of the most valuable points for discussion. 1. Quantum material switching and its implications for speed. The ability to switch between insulating and conducting states on demand using a technique called thermal quenching is a remarkable breakthrough. Currently, processors operate in the gigahertz range. This discovery suggests that electronics could operate at terahertz speeds. The potential increase in speed is not merely incremental but transformational. It raises critical questions about how this advancement might redefine computing tasks, data processing, and the capabilities of electronic devices. For example, how will applications in artificial intelligence, real-time data analysis, and other high-speed computing tasks evolve with such improvements? 2. Replacement of silicon components. The research suggests that this new method could allow for the replacement of traditional silicon components in electronics with smaller and faster quantum materials. This point opens up a discussion about the limitations of silicon-based technology, particularly as demand for faster and more efficient computing continues to grow. It also raises questions about the potential environmental and economic impacts of transitioning to new materials. What challenges might arise in the manufacturing processes of these quantum materials compared to silicon? Furthermore, how could this shift influence the semiconductor industry, which has long been dominated by silicon? 3. Stability and practicality of quantum states. One of the most significant achievements of this research is the ability to maintain a programmed conductive state for months, a feat that had not been accomplished before. Stability in quantum states at higher temperatures is crucial for practical applications, particularly in consumer electronics where reliability is paramount. This stability could lead to new types of electronic devices that are not only faster but also more reliable and energy efficient. What are the broader implications for device design and the potential for integrating such materials into existing technologies? Additionally, how might this influence research directions in quantum computing and materials science? 4. Engineering challenges and new paradigms. The discovery simplifies the engineering challenges associated with using multiple materials for conducting and insulating properties by allowing for the use of a single material controlled by light. This point invites a deeper exploration of how this innovation could streamline the design of electronic circuits and devices. What new paradigms in electronics design could emerge from this capability? How might this influence future research in other areas such as nanotechnology and flexible electronics? Moreover, it raises questions about the potential for integrating these materials into existing infrastructures and what innovations might follow as a result. These 4 points illuminate the profound implications of the Northeastern University research on quantum materials, showcasing both the technological advancements it heralds and the broader impacts it may have on various sectors, including computing materials science and electronics engineering. Each point facilitates an exploration of not only the immediate benefits but also the long-term societal and economic changes that could arise from this groundbreaking discovery. 1. Theory of relativity. 1905, Albert Einstein's theory fundamentally changed our understanding of time, space, and gravity. The theory introduced the concept that the laws of physics are the same for all non-accelerating observers and that the speed of light in a vacuum is constant regardless of the motion of light sources. This led to revolutionary advancements in physics and technology, influencing everything from GPS systems to modern telecommunications. 2. Discovery of penicillin. 1928, Alexander Fleming's accidental discovery of penicillin marked the beginning of modern antibiotics. This breakthrough not only transformed medicine by providing a means to treat bacterial infections effectively but also paved the way for the development of other antibiotics and antiviral drugs. The impact of penicillin on public health has been profound, saving millions of lives and changing the landscape of healthcare. 3. Invention of the transistor. 1947. John Bardeen, Walter Brattain, and William Shockley invented the transistor, which revolutionized electronics by allowing for smaller, faster, and more efficient devices. The transistor is a fundamental building block of modern electronic devices, facilitating the miniaturization of technology and leading to the development of everything from computers to smartphones. This invention has played a crucial role in the information age, transforming industries and everyday life. The recent breakthrough in quantum materials research at Northeastern University presents a compelling future outlook for electronics and computing technology. The ability to switch the electronic state of materials on demand, specifically transitioning between insulating and conducting states, could lead to electronic devices that are not only significantly faster but also more efficient than current silicon-based technologies. Predictions for the future. 1. Terahertz processing speeds. Current processors operate in the gigahertz range, but with the newfound capability to enable terahertz speeds through thermal quenching and light manipulation, we may see a new era of computing. This enhanced speed will facilitate rapid data processing, making tasks like AI computations, real-time data analysis, and complex simulations much more efficient, leading to advancements in various fields such as healthcare, finance, and scientific research. 2. Quantum material adoption. As researchers develop materials that can be more easily manipulated at practical temperatures, the adoption of quantum materials in mainstream electronics is likely to accelerate. In the next decade, we may witness a gradual phasing out of silicon-based components in favor of these advanced materials, which will allow for reduced size and greater functionality in devices from smartphones to supercomputers. 3. Reduction in material complexity. The ability to use a single material that can switch states means a simplification of electronic device architecture. This could lead to fewer manufacturing steps, lower production costs, and a decrease in the environmental impact associated with the extraction and processing of multiple materials. Future devices may be lighter, more compact, and less resource intensive. 4. Enhanced stability and longevity. The breakthrough's ability to maintain a programmed conductive state for months at near room temperature represents a significant advancement in stability compared to previous methods that required extreme conditions. This stability will make quantum materials more viable for consumer electronics and long-term applications, potentially transforming how devices are designed and used. 5. Integration with quantum computing. The discoveries at Northeastern could serve as a bridge between traditional computing and quantum computing. Enhanced control over material properties opens the door for developing quantum qubits that can function at higher temperatures and with greater stability, facilitating the wider adoption of quantum computing technologies. 6. New paradigms in information storage. The quest for faster, denser, and more efficient information storage solutions will likely lead to innovations in data architecture. With the ability to rapidly switch states, quantum materials may enable new forms of data storage that surpass current flash and hard disk technologies, leading to ultra-fast access and retrieval times. 7. Broader implications for electronics design. The research underscores a shift in how engineers and designers approach electronic systems. As the limitations of traditional semiconductor technologies become more pronounced, the move toward quantum materials will inspire new design philosophies and methodologies focused on harnessing quantum effects for practical applications. 8. Impact on AI and machine learning. The increased processing speeds and efficiency could significantly advance machine learning algorithms and artificial intelligence applications. Faster computations will allow for more complex models and real-time data analysis, enhancing AI's capabilities in various sectors such as autonomous systems, healthcare diagnostics, and personalized services. 9. Regulatory and ethical considerations. As electronics become faster and more powerful, there will be a need for regulatory frameworks to address the implications of these advancements, particularly in terms of data privacy, security, and the ethical use of technology. Policymakers will need to engage with technologists to ensure responsible innovation. 10. Global competitiveness. Countries and companies that invest in the development and commercialization of quantum materials will likely gain a competitive edge in the global technology landscape. This could lead to shifts in economic power as new leaders emerge in advanced technology sectors. Conclusion. The discovery at Northeastern University heralds a transformative shift in electronics and computing with the potential to revolutionize how we design and interact with technology. As researchers continue to refine these quantum materials and their applications, we can anticipate a future where electronic devices are faster, more efficient, and capable of performing tasks that today seem impossible. The next decade will be crucial as we transition from traditional silicon-based technologies to an era defined by the remarkable capabilities of quantum materials.